Today we will be simplifying radical expressions that involve quotients. So we will have fractions that we will be dealing with. So example 5 starts with simplifying fractions within radicals. So what we do here is we just divide it into the numerator and denominator and simplify each one individually. So we do the square root of 11 over the square root of 49. And remember, to simplify radicals from yesterday, you just see if there's any perfect squares that will go into it. Nothing will go into 11, so it stays as the square root of 11. The square root of 49 is 7. We cannot go any further since 11 has nothing that will go into it, so our answer is simply square root of 11 over 7. Our second one here, we have the square root of 25 over the square root of b to the 4th. Square root of 25 is 5. And yesterday we talked about how that tells you how many b's or how many variables you have, and then they have to have pairs to come out. So the square root of b to the 4th would be b squared. The other way you can look at it is simply this. If I can get my pen to go where I want it. If you look at the exponent, if it's a perfect square, all you do is take the square root of it. So the square root of 4 is 2. So that's another way it will work, but only if it is a perfect square to begin with. Our next ones are simplifying radicals by dividing. So if we look here, we can simplify the fraction first and then take the square root of it. So if I look here, 11 will go into 88 8 times. So I'm looking at the square root of 8. Then ask yourself, is there any perfect squares that will go into it? Yes, 4 will go in there twice. 4 is the perfect square, so we're going to bring it out by taking the square root of it. So the square root of 4 is 2 square root of 2. And that's your final answer because no perfect squares will go into 2. Our second one here, 3 will go into both 12 and 27. 3 will go into 12 4 times. I'm going to rewrite that. 27, 3 will go into it 9 times. A cubed divided by a. Remember, when we divide, we subtract the exponents, and the leftovers go where the bigger exponent was, so this would be a squared. So I currently have left the following: the square root of the quantity, 4a squared all over 9. And now, since it can't be simplified any further, I take the square root of the numerator and square it as the denominator. The square root of 4a squared would simply be 2a. The square root of 9 is 3. It won't simplify any further, so that would be your final answer. Our last one here is called rationalizing a denominator. It says to multiply the numerator and the denominator by the same radical expression. Choose a radical expression that will make the denominator a perfect square. The reason we use this is because a fraction is not simplified if there is a radical in the denominator. So if I look at this first one, there's no perfect squares that will come out of 5. So I'm left with a radical in the denominator. It is not simplified because you cannot stop when there is a radical in the denominator. So what you do instead is you do what's called rationalizing the denominator. Multiply the numerator and denominator by the same radical expression. So on this one, I'm going to choose to take this times the square root of 5 over the square root of 5. And the reason this works and doesn't change the final answer is because the square root of 5 over square root of 5 is actually equal to 1. When you take something times 1, it equals the same thing. It might look different, but it will equal the same thing. So my numerator, 2 times the square root of 5 is 2 square root of 5. Square root of 5 over square root, or square root of 5 times square root of 5 is square root of 25. 2 square root of 5 does not simplify as the numerator. Square root of 25 is 5. That does not simplify any further, so my answer is simply 2 square root of 5 over 5. If you notice there, it is now in simplified form because there's no perfect squares that will come out of this 5, and there is not a radical in the denominator. Our second one here actually has 2 ways that you can solve it. The first way, if we look at it exactly like how we did the first one, I just took it times whatever was in the denominator. You can always do that method. So if I do that, I'm going to take it times the square root of 8n over the square root of 8n. Remember, you have to take both the numerator and denominator times it. The square root of 7 times the square root of 8n gives me the square root of 56n. Square root of 8n times square root of 8n is simply 8n. 56 can be broken down to 4 times 14. The square root of 4 is 2, so I have 2 square root of 14n over 8n. There's not a perfect square that will go into 14, but 2 and 8 will simplify. They're both outside of the radical. 2 will go in there once, and 2 will go into 8 4 times. So my final answer here is the square root of 14n over 4n. I cannot cancel out these n's, and I can't simplify 14 over 4 any further because one's under a radical and one is not, so they are not like terms. The second method is to do this. It says up here that you want to make the denominator a perfect square. Well, I know I could take 8 times 2 to make it 16, and n times n to make it n squared. So instead of just using what is in the denominator every time, if you want to keep the number smaller, this would be the method you would use. You have to make it a perfect square. So taking 8 times 2 would make it a perfect square, and n times n would make it a perfect square. So now if I solve it using this method, I get the square root of 14n over the square root of 8 times 2 is 16. N times n is n squared. The square root of 14n does not simplify. The square root of 16 is 4. The square root of n squared is simply n. So if I look here, I have 2 n's. That makes one pair of n's that can be moved out. So if you notice here, both my answers or solutions are the same. In one, I used what was in the denominator. It gave me bigger numbers that I had to simplify more. It gave me more steps. But the second one, I had to make sure I knew how to get a perfect square in the denominator. You want to make sure you know what makes something be in simplest radical form. The radicand has no perfect square factors other than 1, so you can't leave any perfect square factors in it. The radicand has no fractions. So remember, that's the number underneath the square root symbol. And the denominator cannot have a radical. Go ahead and complete your quick checks for this section and look at your schedule for your assignment.